Does that look right?
That looks good.
Okay, yep. Because I cannot see my slides and everyone else at the same time. So if someone could do queue management for questions, that would be amazing.
We'll do that.
Okay, thank you very much. So welcome everyone. My name is Ian Sweat. I work at Google. I've been involved in Quick for about 8 years now, prior to it ever being run on the actual internet. I'm a TL for Quick, as well as I'm editor on the IETF drafts. So yeah, what I'm going to focus on today is Quick CPU performance, and additionally HTTP3 CPU performance really in this particular workload, and whether HTTP3 can be as efficient as HTTP2 and 1.1. Let's start with a little intro on what they are. I don't want to spend too much on this since it is a quick workshop, but it's always good to remind ourselves. So Quick is a transport. It's always encrypted end-to-end. A key feature is it has multi-streaming with no head-of-line blocking, including bidirectional streams and unidirectional streams, both of which are used by HTTP3. Zero RTT connection establishment provides a minimum amount of latency where you can send a request immediately instead of waiting for a handshake in order to send a request. And prior experiments at Google showed that this alone was a pretty big win in terms of user experience for sites like search. In our experience, it has better loss recovery, and at least at Google, we have fairly flexible congestion control. So that's really helped us with workloads like video delivery, where we seem to be able to achieve a little bit higher QE quality of experience, than with TCP and HTTP 1.1. It does support mixing reliable and unreliable transport features. So an easy example is recently, the working group decided to accept the datagram draft. The datagram draft is a purely unreliable mechanism, but it can be operated over the same connection as HTTP3 or any other reliable application. But it's also designed with improved privacy and reset resistance, in particular versus TCP and TLS 1.3. Another nice feature that's fairly new, but was designed kind of in from the ground up, is connection migration. So connection migration, the easiest example is, I'm on a phone with cell and Wi-Fi, and I want to migrate from one to the other without interrupting the connection and having to kill any ongoing searches, so on and so forth. So that trying to do connection migration while at the same time preserving privacy was a major challenge for the Quick working group, but something I think they did a really good job at coming up with a good product in the end. So one way of thinking about Quick is just it's an alternative to TCP for TLS that provides reliable delivery. So early on, Google did HTTP over Quick. It is now called gQuick. At the time the project was started, Quick was just the name of the project. And so sometimes people confuse HTTP over Quick with HTTP3 and all these things. But for the sake of argument, it's better to think about gQuick as just HTTP over Quick as like a monolithic piece, even though it really was not. But it was based on HTTP2 actually at the time, and that's kind of where the Quick working group started as well. Even though in the end the divergence from HTTP2 was so large that we ended up calling it HTTP3, and it really doesn't share many of the same primitives, even though it shares the same feature set. One key thing to note here is, unlike IETF Quick, Google Quick used Quick Crypto. Quick Crypto was a new crypto handshake that we are still using today, at least in some amount of production traffic. And it was not a standard. It was invented by Adam Langley. To my knowledge, it was the first crypto handshake that had zero RTT resumption at the time. And so that was its kind of major innovation. The nice part about it is it's very simple, relatively speaking. It doesn't have a big feature set. The negative is you cannot do nearly as much with it as you can with TLS. And additionally, it's not an IETF standard. So the decision was made when it went to the IETF to replace it with TLS 1.3. And as I alluded to before, HTTP over gQuick or just Quick was replaced with HTTP 3 over IETF Quick with TLS 1.3 inside of it, all on top of UDP. So in terms of status, the IETF specifications are in progress. RFCs, I guess, are likely in 2021. I originally had hoped it would be 2020, but people tell me that I'm massively optimistic in that regard. Apple has implementations, Facebook Fastly, Firefox F5. There's a lot of Fs there. Google, Microsoft. There's a variety of server deployments that have been going on for a while. For example, Google has it deployed for all first-party sites right now. So like, YouTube.com, Google.com, so on and so forth, all enable IETF Quick. And, a variety of clients are in development. Since I obviously work at Google, I'll highlight that Chrome is now experimenting in Chrome Stable. So far, the experiments actually look very good. It's not quite done because we do not have 0RTT in Stable. But except for lacking 0RTT, it's looking pretty darn complete. And I can't say that we found a ton of major issues in that process. Well, with our deployment, but not with the specs. Yeah, so I'd like to pause there. That was a lot of background information just on both Google Quick and Quick in general. And, I didn't know if anyone had any questions, whether it's about Google or about Quick.
For any questions, please raise your hand.
Lucas.
Hey,
Raise
Ian.
your hand.
Thanks for the intro. So a question I've got has kind of come from some recent chatter in the IETF group about versioning and stuff like that. So I wondered, like, Google's position is not completely unique. There are some people who've supported G-Quick and IETF Quick, but with your experience in that, like, and as we might look towards evolving Quick, what maybe have you got any insight into the challenges of trying to support multiple versions and extensions on the top of that? Like, testing was mentioned by David Skenazy of like the way that you created your testing framework meant you had to test everything for every version.
Yep.
I wonder, like, for other implementers, like, what might we need to look out for in the future?
That's a great question. So we made a variety of mistakes, and I can relay a few of those. But we test everything with every version, at least for end-to-end tests in general. So like almost, and most other tests as well are all version parameterized. And so as such, if you have 7 versions, you're running 7 times as many tests. In some cases, we actually run like all combinations with each other, but we stopped running all combinations because obviously that's just became insane. And anything that's flaky just becomes enormously flaky. I would say once you add multi-version support, it's really not that bad to maintain it. The marginal cost of maintaining it is relatively low. If you have a few key methods where, it basically like kicks back an array of like the listed versions, and you have another method that like kicks out the alt service and so on and so forth. So once you've kind of invested in that, it's really not that painful. But the first time you add that second version is like a ton of work. And it's fairly easy to get wrong. So obvious things are just like, make sure, something sensible happens with version negotiation. Another one we've run into a lot of problems with is we originally in Chrome did not, if the version changed, we would actually reissue the same bytes, not the same request. And that meant that a whole set of on-the-wire changes were like completely incompatible because you'd send, one version of a request with, at the time actually, when we very first started this, I think H2 hadn't been finalized and HPAC wasn't done. And so we were actually like a big Z-loading it or whatever like Speedy was doing. And so you send it in that format and then you resend it in HPAC, and obviously that doesn't work. And so you really need your framework ideally to like have the original request stored and like go all the way back up the stack and reissue it for things like version changes. So that caused us a fair amount of pain for a long time until we just bit the bullet and kind of changed how we deal with the client stack. So that's a particularly, if you aren't doing that already in your testing framework, I would definitely recommend that. But otherwise, it's gone fairly well. Trying to think, the other thing we've done is that has gone poorly is if you make a quote unquote minor change to an existing version, it can be very difficult to reason about like what will actually happen in the wild. And additionally, you can convince yourself, most importantly, you can convince yourself that this minor change is actually a no-op when it is not. And your testing framework will commonly reinforce this for you because you change both the client and the server at the same time. And you won't notice that if you only change one or the other, that everything breaks. And so not only do we flag protect changes, but we now have some tests where we run like the client without any flags enabled and the server with all flags enabled and vice versa to make sure we don't inadvertently like break an existing version with a change that we think is not breaking. So that was definitely, we've done that multiple times and it's painful. And it's very hard to debug.
Thanks for the answer. This is very interesting.
Ian, you have a question from Zoom from Christian Timmerer that who's asking, what means deployed in detail? Does this include the full feature set or a subset? If the latter, is there an overview of who has deployed what? I
think the interop matrix actually is probably we're deploying basically what's on the interop matrix for like the Chromium implementation modulo. Like, I'm trying to think. I think that's pretty much exactly it. I think 0RTT got disabled temporarily again, and we're going to re-enable it. But except for that, so we're missing key update at the moment. That's kind of a big gap, and that's unfortunate. And then there are a few gaps with path challenge, path response that I'm aware of. Otherwise, it should be a complete implementation. Also, we have an ACK ECN frame, but we do not read or send ECN marks, partially because our clients currently don't have those available to them. We will probably work on that, but after obviously key update and some other critical features. So the list is pretty short, but yeah, the interop matrix is probably the most up-to-date concept of where we're at. And Lars manages that, so if you need to know where that is, then ask Lars.
Any other questions? Okay, I guess we'll let you continue.
Okay, thanks. So now I want to go into the background, not of Quick, but of like the problem that we're trying to solve at Google. So the target workload is Dash video streaming, so aka YouTube. There are some other workloads as well, but that's the primary one. The status quo is that we were actually using HTTP 1.1 over TLS. We were not even using HTTP 2. One of the reasons not to switch to HTTP 2 is that had a CPU cost, and the team who deployed these servers was pretty CPU sensitive. So Dash clients send a sequence of HTTP requests separately for audio and video. There's an AVR algorithm that decides what format to request. So analyzing like the user metrics is a little complicated because you have multiple control loops like interacting with each other, but largely this is straightforward. And the key thing is to improve the quality of experience. So like early deployments showed that the quality of experience of Quick was quite a bit better. So originally it was something like 30% fewer rebuffers. This actually decreased over time somewhat, partially because TCP actually did get better over that time. That was around the time when RAC was being deployed. And also to improve this CPU efficiency so we could do more Quick. So at the time we started the CPU optimization project, we were only able to enable Quick for about half of Chrome because anything more would have just like crushed the servers and blown them out of CPU. We really wanted to enable Android, iOS, and obviously all of Chrome and everyone else. Cool. So in 2017, we were around 2 times that of HTTPS 1.1. By 2017, we actually had enabled all of Chrome. But earlier on, we could only enable a half because we were more like a 3.5x multiplier, which is pretty painful. And even that's an improvement over the very early versions, which were not optimized at all. So obvious fixes reduced the 3.5x to 2x. Look at the most costly functions, figure out if you can cache the return value. Don't allocate data at all on the data path if you can ever avoid it. So ideally, there's 0 allocations per packet being received or sent, at least on average. Minimize the number of copies. This has varying value in different environments, I'll tell you. Some environments are memory bound and some are not. And it's incredibly difficult from a profile to tell you whether it's memory bound or not, at least in my experience. So sometimes you just have to make the optimization and see if it helps. And we added a ton of workload-specific data structures that were optimized for QUIC and QUIC's usage pattern, opposed to more generic ones. But this is really just like iteration. This is just straight up engineering, like look at a profile, make an improvement, roll it out, see the profile change, pick the next thing off the list, and keep going. So, this is just like good engineering. So one challenge here is we had to keep QUIC running while we were supporting multiple GQuick versions, and now while we're supporting IETF QUIC versions, including, I say 2 versions of the invariants, but that's actually kind of like 3, because the GQuick, the first invariants, and then the newer invariants. At the same time, QUIC was also a third of Google's egress. So this is a bit like changing the tires while driving. I mean, you have a very high performance production service that's critical to YouTube and Google. You need to keep it working. You don't want to have to turn anything off. You don't want crash bugs, but you're also trying to rapidly iterate and improve CPU performance as quickly as possible. So there are some extra challenges here. The library that we're talking about, the QUIC library, is actually maintained both by the Chrome team and by the internal Google team. And it's also used by Envoy. So it has a lot of interfaces and a lot of visitors because the Chromium environment in particular is extraordinarily different from the internal server environment. And Envoy is more like the internal server environment. And so obviously like C++ interfaces, visitors, like these are all anti-patterns from a CPU optimization perspective. So we'll get to like what we did to try to mitigate those costs, but there are still some extra costs there. And I would say that, just due to the wide deployment of the library, I'm sure that one could make a slightly faster implementation if you just got rid of all the virtualization. So our library is also very flexible. We have 4 congestion controllers. We have 2, actually we have 3 different crypto handshakes. I forgot about one. At the time we had 2, now we have 3. Many experimental options, probably something on the order of 100 between congestion control, loss recovery, path MTU discovery. I just go on and on. So all these things are just extra branch points, extra complexity. And a lot of them had been very valuable in terms of like being able to iterate. But it's just a lot of extra code. And also it was not really originally written with CPU efficiency in mind. Initially when we started this project, we didn't even know if this was going to work. Like, I will be totally honest. Like the manager who told me about this project said, you know what? I think this is like 60% chance this is not going to work, but we might as well try. And it was like, okay. So as a result, like, correctness and application performance mattered, and CPU efficiency was like a thing you dealt with later, which was in 2017 that later, kind of hit. So let's kind of go over like where the cost actually went. So sending UDP is obviously number 1. We'll talk about that in a lot of depth later. Serializing data, which involves copies and a few other things, was number 2. That'll also get a lot better, and there's kind of a before and after at the very end. Packet processing, which includes receiving packets, was kind of the 3rd one. There's an infrastructure quirk of the deployment at the time, which is very Google specific, but we were proxying from one binary to the other. That cost a fair amount of CPU, as well as costing a fair amount of kind of context switches and other like thrashing. App processing was still pretty costly. Crypto, as you can see, at least at this time, it was not a major cost. We can talk about where it is kind of heading in the future. There's some just overhead from like alarms and being in the server that and backends and stuff, and some other stuff. But we kind of attacked mostly the first 5. sending UDP, serializing data, packet processing. We got rid of proxying, and we optimized our ACK processing. So I want to go over some CPU rules of thumb, because unless you're a hardware person or like very, very familiar with like kernel code and such, you probably would have no good reason to kind of have a concept for some of these. But modern CPUs have many different layers of cache, and they're very complicated. And it's very easy to write code that does not run quickly or is very difficult to run quickly on a modern CPU, just for no obvious reason. So a register lookup typically takes 1 cycle, but you only have 32 of them. L1 cache takes a few cycles. You have 32K. A branch misprediction is around 10 cycles. L2 cache hit is about 128K, which is 10 cycles, which is 128K, 256K. L3 is 100 cycles. Main memory is 250 cycles, sometimes more if it's on the other CPU. And so the thing you just really need to get here is like there's multiple orders of magnitude in latency between like having something in a register or L1 cache versus having to go fetch it from main memory that's like more closely associated with like the other core or the other socket. So spatial locality and temporal locality matter a ton. So spatial locality is if I access, these 16 bytes, the CPU is more likely to think I'm going to access the adjacent 16 bytes than anything else, basically. And that's partially just how the memory page management works. And temporal locality is just like if I access it now and then I access it again a moment later, it's probably in the register or in L1 cache still. And it's very, very cheap to access it again. Whereas if I access it now and then access it, 2 milliseconds from now, like maybe it's an L3 cache if you're lucky. So these matter a lot. So the cool part for programmers is modern compilers and CPUs do an awesome job of hiding all this latency. So compilers do inlining, they reorder instructions, they'll devirtualize like virtual methods in C++ and other languages. The CPU does cache prefetch, branch prediction. So the goal is not to do all these optimizations yourself. The goal is really to make this easier for the compiler. So your goal is to try to write code that is easy for the compiler to optimize, or even possible for the compiler to optimize instead of impossible. So, there are other things that you can do as a developer if you really want to be clever. Like there's something called temporal memory instructions that don't actually move it into main memory and only move it into cache. But optimizations like that tend to be extraordinarily difficult to get right and extremely dependent upon workload. And so in my experience, you're better off trying to make your code easy to optimize than you are trying to use prefetch and like temporal operations, just as an aside. Cool. Why don't I stop there and see if anyone has questions on that, anything I discussed there.
I see one raised hand.
There's one raised hand. Srini, go ahead.
Hi, Ian. So this might be kind of a basic question, just trying to dig into that pie chart that you showed us there. So could you elaborate a bit more on just the costs in terms of, so first of all, maybe a few basic questions. So the sending UDP part, is that most of the time just spent in the Linux kernel, correct? Is that actually,
yeah,
is there anything you can do about it as the quick developer?
It's time that this pie chart was specifically taken from a pprof flame graph that I had. So is time spent in the kernel according to the application's perspective. However, that might actually be slightly undercounting the amount of time that the kernel actually spends. And so if you look at the overall system CPU, it's a little bit higher than 25%. So that's probably actually an optimistic number. It's probably more like 35% or so. But this is from the application profile perspective. But this is all like send message on down.
Got it. Okay. Okay. So it definitely seems like having some optimizations for just the UDP code paths within Linux would actually be highly beneficial. So that's something I understand from this. Okay. I guess as a follow-up, so could you also explain what you mean by packet processing? Like, could you elaborate on what that actually entails?
What is packet processing? Packet processing in this case is receive message, decrypt. It is processing stream frames, like data frames. It basically is anything in the receive pipeline, but I subtracted out ACK processing because ACK processing by itself was such a large component that it was worth splitting out. But basically anything under the receive MM message call stack on up, I considered packet processing. So that's kind of how I did this. So it's kind of a lot of things, but it's generally the receive side. But I mean, one of the big things to take away from this just is that in general, like sending is a lot more costly than receiving. Yeah. Oh, and I did crack out decrypt actually, because the crypto does include the symmetric operations for both encrypt and decrypt. But the decrypt operations, at least on a server, are so small it's like not in this workload, at least, it's almost not relevant.
If I might just ask one or a comment, like one more thing. So the crypto, I mean, I'm a bit surprised. So one of the things that people typically try to accelerate is crypto, but it seems like that wouldn't be as beneficial for Quick because it's just like 5% of the time. Am I understanding this correctly?
Yes, but later in the slides, I will tell you that your initial intuition is correct, and it is still worth optimizing crypto. It's just not worth optimizing crypto until you've also dealt with the packet sending costs and other things. So we're now at the point today where like optimizing crypto is the right thing to do, but until you've gotten through some optimizations for packet sending and like sending fewer ACKs and things like that, it's sort of like not worth it. So this is it's definitely worth keeping in mind. This is 2017, and that's 3 years ago. And so thankfully we've like made a huge amount of progress, and things are in a much better place. But at the time, you're right. At the time, optimizing crypto would have been a waste of time because you could have saved more money by or more CPU by like optimizing ACK processing. So they were lower.
Okay.
Yeah.
Okay, that's helpful. Thank you.
You're welcome.
Michiu?
Can I just speak here?
Yeah.
Yes.
Okay. That's a quick question. So I assume this is say the reasonably long-running connection, say exchanging multiple data over and over on the same connection. So do you do something like header prediction in Quick? And if you do, what's the effect of that?
Header prediction. I think
like TCP, yeah, the TCP basically is when you see the packet and based on timestamp value, etc. Then they speculatively assume like, okay, this packet must be this. Okay, let's do fast pass kind of thing, right? So that's Quick to this kind of thing.
Our implementation now does. I'll outline a few cases when we do that specifically in the next few slides, actually. But at the time we did not. But now we do a variety of TCP style. We didn't really call it header prediction, but we basically optimized for cases when packets are received in order and acknowledged in large batches, things like that.
Okay, thanks.
Cool. A good question.
And there's Jenna in the online.
I was just going to ask a similar question, clarification on this point. Excuse me. So this is on which traffic, Ian? To go back to the original question that Srinivas was asking, talking about 5% crypto here, this crypto is dominated by symmetric crypto, not by the handshake. Is that a reasonable?
Yeah, because this is like the Dash video serving workload where.
Right, but on the other hand, if this was like a web page or Google search, for example, that crypto cost might look quite different.
Yeah, so I'll tell you just anecdotally, like if you look at the Quick CPU cost for things like Google search and like that kind of more generic, like smaller object workload, the CPU difference between Quick and HTTP2 it's hard to tell. Like it's not obvious that there's any whatsoever. Even in 2017, the difference is small enough that it was not a dominating factor. So in that environment, it's nice, more efficient is always better, but it wasn't driving a ton of work.
I'm with you. I'm just saying that the cost of crypto as a fraction of total cost would have been probably high in both HTTP2 and in HTTP3.
Yes.
Simply because the handshake cost is going to be public key crypto, and that should cost more. And just speaking to the point that crypto is a cost, but there are different pieces of the crypto that are more or less expensive. Thank you.
Yeah, the handshake cost on small object content is actually substantial. Yeah.
So I want to remind people that there's quite a few slides left, if I remember correctly, and maybe let's go through a few more questions quickly, and then let Ian make some more progress, because as he said, this is the state of 2017, and he wants to talk about the stuff that has happened since.
Yes. Quick one. I've always wondered. You say CPU is 2 times. Does that mean you buy 2 times as much hardware to be able to support Quick? Or I think the real question is how much of this is in the total workload of the servers? Like, if this is all just 1% of all that the servers are doing, it's not that big of a deal, right?
It's at the time it was a substantial fraction. So I think I think a rule of thumb is that probably around half of the CPU was used in serving bytes, and the other half was used in cache management and other things. I don't know the breakdown exactly off the top of my head, but it was substantial enough that it's not like we changed 1% to a 0.5%. It's more like we changed 60% to 30% or something.
But that means that your actual costs in the data center were hugely increased with Quick. How did you validate that economically? How was that worth it economically?
So the way we rolled it out is, as we made CPU improvements, we increased the amount of traffic that we were using Quick for over time. So we always have some extra CPU envelope, anywhere. We have some headroom, and so early on we used the headroom that was easily available. And then, once that got to be close to a pain point, then we stopped ramping it up and started optimizing and gradually ramped up as we had more headroom. So, when you buy machines, there's a certain amount of disk memory, CPU, everything that kind of ends up being configured. And at the time, there was excess CPU on the machines that do Dash video serving for YouTube. There was just extra because we were typically disk and NIC bound. That's less true now, but yeah.
Okay, makes sense. Thank you.
Okay, one more quick question, Viti.
I just want to ask in the last slide you showed there's cache prefetching, and that probably works in the kernel, right? Does it work in the user space?
Sorry, what?
The cache prefetching, yeah.
You mean trying manually to do cache prefetch instructions?
Yeah, it can be done in the user space. My question.
Yeah. Okay. Yeah, no, it can be. There are prefetch, at least in C++, there are prefetch instructions for L2, L3 cache, and they do work. They're very difficult to get right. The one case we found that I think we actually had a prefetch instruction for was if you had blocks of memory and you knew you were going to read from this block of memory that's 16K, and then you were going to read from this block of memory that's 16K. If you knew you were going to read the next one, then you can prefetch the very beginning of the next one. But optimizations like that are very brittle, and by the time we reevaluated whether that was actually helpful, it stopped being helpful, and we don't know why.
Okay. Yeah, it's like if you get a list of packets, like stream frames, especially when you're doing perf test, right? Then all the frames are 1500 bytes, the whole packet. So if you can prefetch the list of packets before you read them, I think that would be useful, but I just didn't know that you could do it in the user space.
Yeah, there you go.
Thank you.
At least on Linux, without special permissions, yeah.
Cool, thanks.
Should I move on since we're running low on time, or is there anyone else?
Yeah. Okay. No more people in the queue.
I can make it through all the rest of the slides in one go, just to make sure we can do all the questions at the end. So sending and receiving UDP, well, I'm going to stop once more, but is obviously very critical to this. Why is it so critical? So UDP sending is 25% of the CPU in our workload, although as I said, it's probably really higher because 25% doesn't count the full kernel time. It's greater than 50% in some environments and some benchmarks. I've seen profiles that show it's greater than 50%. Lars has a nice paper coming up later today that also talks about a similar number. And UDP send message, at least when by itself, is about 3.5 times the cycle per byte of TCP in Linux. That's assuming you do fairly large sends, like 64K, 16K for TCP. And so a huge portion of that gap is just the size of the packet, but still it's a huge gap. An UDP send M message allows you to send multiple messages at once, which you think would help a lot, but it doesn't really, because it mostly just saves the syscall, at least in Linux. So some of these things may be Linux-specific quirks, but the point is that there was no real fast path at the time for like sending a large amount of data into the kernel. So then came UDP GSO. It turns out not only was GSO much faster than send message, but in ideal circumstances, all in software, it can be 7% faster than TCP GSO, which is great news. GSO is a little bit of it's a little bit of an odd API in the sense that you assemble a packet, which is actually like say 10 quick packets all stuck together and concatenated. And the first n minus one of them, so the first 9 in my example, have to be identically sized, and then the last one can be like a smaller packet. And then the kernel, it passes it all the way down to the stack and can pass it all the way to the NIC driver before it splits them up. So this was much, much faster. The benchmarks mostly show it's around, as you might expect, 3.5 times faster. So it's very comparable to the TCP path, at least for software. However, you also have to take advantage of it. At least at the time we were doing pacing. A lot of the time the pacer decided to send only one UDP packet at once. As you can imagine, this didn't actually help because you didn't get any benefits at all. But even bumping it up to 2 packets at once, where we kind of made it bursty, really helped and greatly improved the CPU benefits. And in some cases, we found we could bump it up to 4 and other higher numbers. But at some point, the retransmit rates definitely do kick in because of the buffer sizes. One detailed note about that, for both Linux and our implementation, if the bandwidth is below 1.2 megabits, we only send 1 packet, even if we otherwise configure like a larger burst size. This actually turns out to be important because there are places, for example, India, where sending like 4 or 8 packets at once is almost guaranteed to result in loss on a lot of networks. Cool. So let's talk about kernel bypass. Bypassing some of the kernel can be a lot faster than UDP sockets on Linux. Lars talks about this in his paper as well, or the paper coming up. DPDK is a full bypass. AFXTP is a new kernel API that's supposedly as fast as DPDK. Google, actually, we use a software NIC, which is documented in the link here, and all the slides will be up at the end, so you can click on links and such. But these are all conceptually very, very similar. They're basically just kernel bypass. The challenge is almost all of them come with a fair amount of increased complexity. Most come with escalated privilege requirements. So at the very least, you might need capnet raw. Sometimes you need root. This typically means you either need a dedicated machine, which is definitely a deployment challenge. For a while, we were actually using packet sockets, and that requires a whole host of extra implementation cost, in our stack that otherwise the kernel would do for you. So you can also put everything in the kernel. I know, that link is actually a link to a Netflix paper about putting TLS in the kernel, I believe. But I know that there are some implementations like Microsoft's that are kind of oriented towards all being in the kernel. And it seems like that approach can be extraordinarily fast. So let's talk about UDP GSO with hardware offload. Fairly soon, actually, after UDP GSO was introduced, NIC drivers started supporting hardware offload. At the time, the last paper I can find was written, at least the Mellanox MLX5 driver and the Intel IXB, I can't pronounce that word really, did support it. And that provides another like 2 or 3x speed up So now the cumulative acceleration is something like almost like 10x of what it was before. And so we've taken our 50% CPU number down to maybe like 5%. So alone with just doing like UDP GSO and like various hardware offloads, we potentially dropped the CPU in some workloads at least by a factor of 2, without doing any core like OS I guess library optimizations or anything like crypto and so on and so forth. So the nice part is this does not require escalated privileges. Increasingly, these NICs actually support this out of the box. And it's a pretty easy feature to use. It just works once you have UDP GSO implemented. The current thing we're working on right now with the kernel team at Google is pacing offload, or UDP GSO with pacing offload. I linked to a patch set there. That allows you, instead of sending, say, a burst of 4 packets and then coming back around a few milliseconds later and sending a burst of 4 packets, you can actually send, say, 16 packets and say, I want these 4 packets to go out 1 millisecond after these 4 packets and these 4 packets and these 4 packets. So things like this allow you to visit connections less often. So you're bringing a state into the cache and like bringing it out of cache. So that really helps like memory, temporal locality. It also allows larger batches can be better for the kernel and it could do more optimizations. It's possible that in addition to GSO offload to hardware, a NIC could actually offload pacing as well. So this API is not yet finalized, but if you're interested in it, definitely take a look. And give Willem van der Bruin some feedback on whether that current API works for you, or benchmarks too. So receiving UDP packets. Originally, we used MemMap RxString, and it was quite a bit faster. However, over time, receive MMS performance improved a lot, and now it's almost as fast. And so much so that the escalated privileges required to run RxString are probably not really worth it in most environments. We use a BPF to steer quick connection IDs to avoid thread hopping. This is fairly critical if you get a lot of NAT rebinding or connection migration. And I have a link down there, but the UDP GRO by itself improves receive CPU 35%. So the gains of GRO is not as large as GSO, but they are present, and for high receive workloads, they could be helpful. I'm going to pause for a moment, but if there are any questions.
We have about 15 minutes left, unless we want to, eat up the break a little bit.
Okay, why don't I keep going now? All right. So next, as we kind of mentioned, was mentioned before, we fast path some common cases. So most of the time, packets are sent in order. Most packets arrive in order. They're acknowledged in large blocks. So we optimize ACK processing for contiguous packets. For example, we would, if stream frames were being acknowledged in 10 packets in a row, and it was all the same stream, instead of like upcalling to the stream that certain data had been acknowledged, we would just acknowledge, upcall all at once. Data receipt, similar idea. We kind of fast path that. And bulk data transmission was actually the biggest single optimization to optimize for the case where we just had one stream frame in a packet. Because a quick packetization code can be somewhat complex if you're trying to pack an arbitrary number of frames into a packet, and you have to deal with every single frame type. But if you're only optimizing for stream frames, you can really make a lot of optimizations, minimize copies, and that saved around 5% of CPU by itself. So efficiently rating, yeah. So it used to be that we actually split up the data ownership, like when we sent packets, kind of like video was kind of implying, where every time we sent a packet, we would take like the stream and chop it up into, say, 1,300 byte chunks. And then we moved to a model where the data ownership was much more contiguous, and it had large buffers, and we just tracked like which data was in each packet. And that was a fairly substantial change, as you might imagine, but it did two things. Not only did it save some amount of CPU and improve memory locality, and reduce data allocations. Made it so basically we had at the very least one fewer memory allocation per packet being written. But it also enabled like memmove sort of operations. So now we can transfer ownership from outside the API, outside the library into the library, instead of doing a copy at that layer. So that both eliminated an allocation and a copy potentially. Cool. So another one is in terms of increasing memory locality. For a while, we had a data structure that was a vector of quick frames, which could be any type of frame. That had a pointer to a stream frame. Obviously, this is bad for memory locality. It's bad for memory allocation. So what we did is we changed it to an inline vector, which had the stream frame case inlined as well. And so now we move to a point where typically for a given packet, like all the memory is like packed in there, and it's all contiguous for all the data structures that we're tracking, like what's in flight. So this is a pretty big one in terms of sending fewer acknowledgements. So acknowledgement processing is expensive. Sending packets is actually pretty expensive, especially on mobile clients. Anecdotally, on like Android and iOS, sending acknowledgements can be more costly than receiving data, even for large downloads. So even though you're sending tiny 50-byte ACKs, they can be more costly than receiving 2 large packets. So BBR works really well in this circumstance because it's a rate-based algorithm and it tends to not run window-based most of the time. And that means delaying an acknowledgement a little bit does not cause it to be window limited usually. So this optimization was a critical reduction to achieving parity with TCP in some of the quickly benchmarks that were blogged about in the link. And it looked like in that case, they were around a 25% CPU reduction. And I and John also have a draft at the IETF, an individual draft, to describe a way that one can request that the peer send fewer acknowledgements. And that allows you to optimize for your specific congestion controller. So this is another case where we're doing something that TCP's kind of been doing for a while. TCP already creates stretch ACKs both at the receive layer, at the middle box layer, and sometimes at the center layer. So another one for us, which was a really nice optimization, was feedback directed optimization, also known as FDO. So because we have so many interfaces, we have a lot of virtual methods, and FDO can devirtualize a huge variety of them, can do prefetch, and it really allows it gives the compiler the best possible information. It allows it to say like, oh, it seems like you always use BBR and you never use cubic. So like, I can branch predict in that direction, so on and so forth. So there's also something called thin LTO, which does cross-module optimizations. But all these things in accumulation are around 15% CPU savings in our case. That's probably on the high side. Probably most binaries would not find it's quite that much. But as I said, because of the way our library is constructed, things like FDO are particularly valuable for us. So if we compare 2017 to today, sending UDP approximately halved. This is with UDP GSO, but without hardware offload, just as a context. The serializing data path got a fair amount cheaper. Packet processing got over half, twice as cheap. Proxying just went away, so that helped immensely. Basically everything got cheaper, but some of these things were such big portions of the mix before. They were disproportionately valuable. So like sending UDP and proxying were obviously a disproportionate part of the improvements. So what's next? Wider support for GSO and similar APIs. So Android, it will come to Android sometime soon, I believe in the next Android release. I'm under the impression that Windows is adding something similar. I know iOS is likely to have something at some point. And getting hardware GSO more widely supported. in theory, this could make, could be approximately as fast as TCP TSO. Another thing that's coming next is crypto offload. So, after you've optimized the UDP send and receive paths, symmetric crypto can be probably around 30% of CPU, based on the SAI paper that's coming up later. And offload on the receive side also enables reordering in the NIC, which can be another potential optimization, since it can enable all those fast path optimizations I talked about before and make sure they're typically used. So where are some open questions here? Because this is not something that's done. Is what is the right API? That's definitely been an open question. To my knowledge, no one's created a kernel API for crypto offload at this moment. Another open question is more offload worthwhile? So is it worth not only optimizing symmetric crypto for send and receive, but is also optimized, say, sending stream frames and chopping up data into stream frames? Currently my intuition is no, because the extra complexity is substantial. But every time you make one optimization, then something else seems much more appealing. But even with symmetric offload, Quick should be about as fast as KTLS, I would expect. And symmetric offload for Quick should be quite a bit easier to implement than KTLS, which has a fair amount of complexity because the record layer of TLS does not match up with the packetization layer, unlike Quick, where the record layer and the packetization layer are the same. Another one that's come up, so IETF Quick added header encryption or header protection, which requires a two-pass encryption approach. So this definitely adds a little bit of CPU cost, and in particular, even though it's only a tiny amount of data that we're encrypting, most encryption libraries are not optimized for like encrypting a single block. So different people at the Quick working group come up with two potential optimizations here. One is to encrypt multiple headers in one pass. So for example, encrypt 8 headers all at once. That was Nick Banks from Microsoft. Thank you. And another one is to calculate header protection. In parallel. Sorry. Actually, I think the second statement is yes. Sorry. It does header protection at the same time that it does the regular AAD, and that's done in Pico TLS Fusion, which is the Quickly implementation, or the stack used by Quickly and Kazuo. So the final question is, will HTTP 3 be more efficient than HTTP 1 or 1.1? And at least at Google, we are not quite there today. We are very close, but there is still a slight premium. But there are a lot of optimizations available to us that we know about and we know will work. UDP GSO hardware offload is like the first one that comes to mind. That's just a matter of having the right mix and getting it deployed, pacing offload. All of these things are very promising. So I'm pretty confident by in another year or two we'll be at parity with HTTP 1.1. Questions?
Thanks, Ian.
Thanks.
Thanks much. Questions?
I see Lucas has his hand up, but I would actually like to participate somebody who doesn't have the chance to talk to Ian every day or every other week. So if there's some questions from the academic community, I'll prioritize them hard over people who hang around the working group. But not seeing anybody else, Lucas, go ahead, get us started. No, Srini again. No, Srini takes. Go ahead.
No, I'm happy to let Luca go first. Luca, why don't you go first?
You go. You have the video up. Come on.
Yeah.
Okay. All right.
Quick then. Let's get me out of the way. I feel stupid. Like you mentioned proxying a few times, Ian, but maybe I missed like what you mean by that, and whether that was something unique to Google or if that's something that like other implementers have and that they don't realize that they're doing or something.
No, this is unique to how we initially deployed Quick at Google, where Quick was only implemented in one binary originally. There's basically like a large content binary and then a binary that's used for all of their serving at Google. And originally Quick was only in the like generic binary, like also known as the GFE from the Snowden leaks. Encryption added and removed here. And so it was only in that binary, and so we had to proxy to the other binary over localhost for a period of time. So it's very Google specific work. Yeah.
Okay, no, thanks. That makes sense.
All right, Srinivas is next.
Okay, yeah, I have a couple of questions. So the first one is, could you talk a little bit more about whether or what kinds of offloads or acceleration should we focus on separately, like on the client side? And I'm talking especially about like mobile clients, and also like on the server side. And I'll ask my second question after you're done with the first one.
Yeah, so today on mobile clients, I think the best options are to look into the newer APIs that are coming to Android and hopefully iOS around like GSO and receive message and the equivalents. So like the bulk send and receive APIs.
Mm-hmm.
In particular, the bulk receive APIs are pretty easy to use, and they've been around for a long time. And they do even receive message is actually a performance improvement over receive message. So those are the kind of most available and lowest hanging fruit. To my knowledge, no one has any sort of hardware offload for UDP on a mobile device today. I don't know if that's going to change or not. I'm not an expert on that. Maybe someone else here has like a better lay of the land for NICs. In terms of crypto on mobile devices, crypto is typically not an issue in my experience because most mobile devices actually have pretty good dedicated crypto offload, at least commonly for AES, GCM. And so the other one is like the ACK reduction or ACK decimation. In the case of iOS for us, that was actually critical for us to be able to actually use Quick for YouTube, just because it was so critical to reduce the number of acknowledgements being sent. Yeah, those ones would be the ones I'd focus on really. If you don't do the ACK reduction or the ACK decimation, you're probably never going to see the full performance you can on a mobile device, is my experience.
Okay, that's helpful. I guess the other question I had was you mentioned that when you have pacing and you're only sending one packet at once, like you lose some of the benefits of the batching based optimizations. But then like later in the talk, you also mentioned that, like BBR uses pacing and, that allows you to actually have that open feedback loop where you can delay the acknowledgements and it wouldn't matter. So I guess I was trying to like understand just in terms of the protocols that you might use, whether that's BBR or Cubic or whatever, like, do you have a sense of what kinds of protocols might actually be more efficient? And, like, so should they, is a pacing-based protocol actually better in some ways, or should we kind of rely on a hybrid of pacing versus sort of burst condition window-based ones? Go ahead.
I think I don't think there's one easy answer to that. The one thing I will say is that the more rate-based, pacing-based protocols that tend to run less window-based tend to be able to take more advantage of the like ACK batching and the ACK reduction because you don't suffer any performance degradation from like being congestion window limited and waiting for like 20 packets to be acknowledged before you can send again, right? So like by mostly operating rate-based, you kind of stay out of that regime. On the other hand, like, but for other optimizations, I don't think it matters as much. It's just that one particular optimization is a little bit easier to do with a non-window-based controller. But the rate you're dealing with also matters, right? So I mean, if you're in a relatively low RTT connection and you're receiving acts of 10 or 20 packets at once, maybe the RTT is only 3 milliseconds. So like, your pacing is going to be very coarse anyway, so it might not matter. So it does depend on the environment, certainly.
Okay, I don't know. Thank you.
Okay, we have Nick, Robin, and Vidi in the queue. So Nick, go ahead.
Ian, you mentioned steering on the receive based off of connection ID and using for NAT rebinding and migration. And I'm wondering, how often do you encounter either of those scenarios in practice?
So migration is not enabled in Chrome, partially because of data usage concerns and such. The apps that do enable migration don't migrate that often, and so we don't see it that often. But we do see NAT rebinding more often than I'd expect. I think the the last time I checked, the numbers were something on the order of like 10% of connections or something were like experiencing NAT rebinding, but I can't say for sure whether like where in the connection it is occurring. So we're trying to get better data on exactly not only the distribution of NAT rebinding, but like how far into the connection it happens, as well as, I shouldn't say 10% of connections. I should say, if you take the number of NAT rebinds and put it over the number of connections, it's around 10%. So I don't know if that's 1% of the connections experiencing a NAT rebind like every 4 seconds or what. And so, yeah. So it does end up being important, but it's not absolutely critical, I would say. I would say the one thing though is you don't want to get that wrong, right? Like if you're always tossing to the wrong silo interface, we did that once. That is absolutely terrible. Like you pretty much cannot operate a quick server if you're throwing every packet across threads and CPUs.
Yeah. Okay, thanks.
Yeah, we're actually going to have NAT rebinding data, I think, the future IETF. So yeah.
Okay, Robin and Vidi. Robin.
Hello, Ian. You kind of left out the most important aspects, which is of course logging. So I was wondering if you could talk about if you log in production and how much overhead that gives and how much percentage of the connections you log, that kind of stuff. Yeah,
so we do logging in production. The percentage varies by service and a few other things, but it varies kind of typically between like 1% and 100%, depending on the service and customer and so on and so forth. That does add some cost, but it's not that substantial, especially when it's around 1%. And so we do have some limits to make sure, for example, if you have like a very long running connection, we don't allow the log to go and become infinitely sized, because obviously like that can cause memory issues, and just like recording the log suddenly causes the machine to like So except for some constraints like that, if you look at a profile, I mean, logging is in the other category, so it's well under 5% of CPU.
Great, and just to confirm, that's still quick trace that you're logging at the server side.
We have two different types of logs. We have what we call transport stats or transport connection stats, which are like just connection oriented, like how much packet loss was there, how many requests were there, like what quick version was spoken, what was the connection close error, some like really coarse logging. And then we have something like quick trace. Yeah.
Thank you.
Okay. Vidi in the queue, and then Srinivas still has his hand up, which means we might go around back to him, but Vidi, go first.
So I have a question regarding one of the slides which talks about hardware offload. I think that's probably for the UDP, right? And my question is, UDP GSO, is it not enough? Like, was the hardware offload give a better CPU usage?
Yeah, so UDP GSO with hardware, like with NIC acceleration to do the GSO on the NIC, yeah, it was around another 2 to 3x based on the existing NICs that have been tested. There's a link to a nice paper by Eric Dumzey and Willem van der Bruin, like that includes some very high level metrics, but it was fairly early on. And it's possible NIC vendors have better numbers, but it's a good bit more, right? It does give you a lot more, and it really makes it very competitive with TCP. Once you have that, and fairly competitive, as I said, with kernel.us.
But does that set a promising result for pursuing the crypto offload as well, like for segmenting quick along with UDP? Yeah.
So I mean, I think of these things as steps, but yeah, once you have a bulk send offload, then doing the crypto offload hopefully becomes a little bit easier, because you're the key association was with like a larger chunk of data. But yeah, I guess I feel like these are steps. First you do like GSO, then you do GSO with hardware, right. And then hopefully we'll get to the point where we're doing like a GSO with hardware and with crypto offload all at once, all on the NIC.
Yep, thank you.
All right, Srinivas.
Okay, yeah, thanks for letting me ask another question. So I'm curious if later down the line, it would make sense to consider offloading even some of the, say, the protocol processing. So
Yep.
this is something, so, for example, say the congestion control loops that many of these protocols actually run, like, and these may not be, sort of fixed function, like these would certainly have to be over kind of reprogrammable substrates. Like, you don't want to lose the flexibility that Quick offers to kind of change the algorithms and iterate quickly. But down the line, would you say that actually makes sense, or would you say like that's?
I would say possibly. It's hard for me to tell how much we'll get with crypto offload, so it's hard for me to answer that question. But I would say you can imagine something like eBPF being used to implement either an entire quick stack or a huge portion of a quick stack, and then compiling that down and running it like on some mixture of the NIC and the OS. I mean, that sounds like really cool research, and it sounds very promising, but it also, I think it would be enormously difficult to get right. At the moment, we don't even have most of our congestion controllers in eBPF or anything like that. So I think it's possible. I think the marginal gains are going to be a lot lower. So I think it's just a question of what they end up being, and it's really hard for me to quantify without just doing it.
That's fair. That's fair. Thank you.
Also, I guess the other thing I'll add is the goal to be faster than TCP, or is it to be like twice as fast as TCP? I mean, if you want to be twice as fast as TCP with TLS, then I think, yeah, sure, like full onboard NIC offload is probably what you're going to have to do.
I think the goal is to become faster than TCP and then make TCP again faster than Quick, and we just keep going.
Yeah. I like that competition.
It's just a never-ending arms race, Ian. So,
All right. Do we have any other questions for Ian? I don't see any hands that are up in the Zoom.
Nope.
Great. Thank you very much, Ian. This was great. His slides will be up eventually on the website, and I might stick them into the Slack if I get them while the Slack is